Hello students. In the last two sessions, we have seen the broad classification of control system, that is the open loop control system and closed loop control system, transfer function, the steps to derive the transfer function, and we also saw a few examples in electrical system and how to derive the transfer function of electrical systems. So in this session, we will be focusing on mechanical systems. Let's move on to the session. In this session, we will be looking into modeling of mechanical system. What are the basic components that are used for modeling a mechanical system and how to write a differential equation governing that particular mechanical system. All these things will be dealt in this session. There are two types of mechanical systems based upon the type of motion. If the motion is going to be linear, then you call it as a translational mechanical system. If the system is going to take angular motion, that is rotational motion, then you call it as rotational mechanical system. In electrical systems, there are three elements basically: resistor, inductor, and capacitor. These three elements are used for modeling electrical systems. Similarly, we have three elements here, that is a mass, damper, and spring. These are the three elements used for modeling mechanical systems. The weight of the mechanical system is represented by mass, which is given the letter capital M. The friction existing in the mechanical system is represented by a damper, which is given the letter capital B, and the elasticity existing in the mechanical system is represented by spring, and the letter used for representing the spring is a capital K. Whenever there is a force acting on this mechanical system, there are opposing forces due to mass, damper, and spring. In the next few slides, we will be seeing what is the expression for opposing force due to mass, opposing force due to damper, and opposing force due to spring. So we also have rotational mechanical system. After discussing translation system, we will move on to rotational mechanical system. So what you see here is the pictorial representation of mass. We have given a small box-like structure with a capital M representing the mass of the mechanical system. If a force F acts on this mechanical system, and if you have a displacement of X because of this force, then the opposing force due to this mass is given the function Fm is equal to m into d square x by dt square. So Fm stands for opposing force due to mass, and the expression is m into d square x by dt square. The unit of mass is kg here. This is the pictorial representation of damper, sometimes called as a dashpot. If force F acts on this system and there is a displacement of X, then the opposing force due to the damper is given by Fb is equal to B into dx by dt. B is the frictional coefficient, which is having a unit of Newton second per meter. So that particular B's unit, you can derive it from the expression itself. So the force has a unit of Newton, and here it is dx by dt, which is nothing but velocity. So it unit will be meter per second when it goes that side, and then becomes Newton second per meter. So this is the second component used for modeling mechanical system. The third one is your spring. When force F acts on the system, then the opposing force due to the spring is given by the name Fk, that is equal to K into X, where K is the spring constant. The unit obviously is Newton per meter. Newton per meter. Similar to translational system, you have three elements in mechanical rotational system also. Damper and spring, both of them, they don't have a different notation. They are the same, that is the B and K. Whereas in rotational system, the mass is replaced by moment of inertia. And the force now will be a twisting force. So it is given the letter T representing the torque. So the input force is torque here, and the displacement is angular displacement. There it was a linear displacement x, now it is angular displacement theta. So instead of mass, you have moment of inertia. This Tj, Tb and Tk represents the opposing forces due to moment of inertia, due to friction and due to spring constant K. So the difference between the mechanical translation system and rotational system, to summarize, it is like instead of force, here it is torque, and instead of linear displacement, it is angular displacement, and instead of mass, it is moment of inertia. Here also you can get the unit of bk by using the expressions itself. For example, here in the k takes the unit of newton meter per radian, because the torque unit is newton meter and theta is measured in radians. So obviously the spring constant gets the unit of newton meter per radian. So first we will look into translational system, and then we will move on to this mechanical rotational system. So these are the steps to determine transfer function of mechanical translational system. The first thing that you have to do is identify something called nodes. Nodes are nothing but meeting points of two or more elements. This is similar to what we do in electrical system, where node is a point where two or three elements get connected. The similar definition is applicable here also. So node is a point where two or more elements are getting connected to that particular point. Usually masses acts as a node points. So for each and every node, you have to write a differential equation. That is, you have to write a force balance equation for each and every node. Force balance equation is like a sum of applied forces is equal to sum of opposing forces. Using this particular theory, you have to write the force balance equation for each and every node. Suppose if you are having two nodes, you have got to write the two node equations. So after getting the two node equations, you have got to write the Laplace transformation of it, and write the algebraic equation equivalent to it. So take Laplace transformation of all differential equations and convert them to the algebraic equations. After doing so, take the ratio of output variable to that of input variable, which will give you the transfer function. So we have seen the steps here to determine the transfer function of mechanical translation system. In the next session, I'll give you some examples and we will solve few problems so that you understand better how to obtain transfer function of mechanical translation system. Thank you.